All right, so welcome back. In the last video, we talked about about the definitions of increasing and decreasing, and then we also did a quick algebra refresher about how to solve a nonlinear inequality. So that brings us now to calculus with that review under our belt, and now we have a process to figure out where a function is increasing or decreasing. We call it intervals of increase or decrease. It's a pretty straightforward 5-step process. First, find the critical values. Now that's like the first step of tons of stuff we do. Find the critical values. Step 2, divide the domain of the function into open intervals according to the critical values. And then step 3 is to choose those test points. Like we saw in the review, we're going to build out a table with our test points, intervals, test points, and then we're going to use the test points to determine where the derivative is positive or negative. So if we want to figure out where a function is increasing or decreasing, we figure out using this table where the derivative is positive or negative. That'll tell us where the original function is increasing or decreasing. So let's hop right in here and see what we can come up with. Okay, so example A, nice polynomial. First step, here I guess I'll scroll back up so we can have our procedure visible. The first step is to find the critical values. So the first thing I see when I look at f, I see a product and I see a composite function. So I suppose you have the option here. You could, multiply it out and get a polynomial and use the power rule a couple times, but I'm just going to differentiate as is. And that's step 1 is to find the critical values. So let's just find f prime. So f prime, let's see, we're going to apply the product rule. So the derivative of the first function is 1. Okay, I guess technically, okay, I'm going to focus on these. So when I say first function, I mean x. Second function, I mean x minus 3 squared. You know what, since this one is a little few moving parts, I'll write out all the little steps. So it's going to be what? Derivative of the first function, which is x, times the second function, x minus 3 squared, plus the derivative with respect to x of x minus 3 squared times the first function x, and of course the derivative of 2 is 0. Okay? Now let's take these individual derivatives. We have 1 is the derivative of x, so you just get x minus 3 squared plus the derivative of x minus 3. Now notice that's composite. The inside function is x minus 3, x minus 3. The outside function is x squared. So the derivative of the outside function is 2x. I'm going to immediately evaluate at x minus 3 and then multiply by the derivative of the inside function, but the derivative of x minus 3 is just 1. Don't forget times x. Okay, so there's our derivative. We want to find critical values, which means we need to solve f prime equals 0. So that's going to give us what? X minus 3 squared plus 2 times, actually it's 2x, sorry. 2x times x minus 3. If I move that x to the front, 2x times x minus 3 equals 0. Factor. I'm going to factor out an x minus 3. They both have an x minus 3 in common, which leaves me with an x minus 3 plus 2x inside our brackets here. Okay. And if we simplify this, we get x minus 3 times what? X plus 2x is 3x minus 3 equals 0. And now you can use the zero factor theorem to set these individually equal to 0. So x minus 3 equals 0, or 3x minus 3 equals 0, which imply that x equals 3. Or that, add 3 to both sides and divide by 3, so x equal 1. So there's your two critical values. Now remember, we have to consider the possibility that other critical values stem from the fact that a function might be not differentiable. But look at the derivative. The derivative is a polynomial. the derivative is a polynomial right here. The polynomial has domain all real numbers. Polynomials are always smooth and differentiable, continuous and differentiable everywhere. So there are no cusps or anything we have to worry about, no asymptotes, two critical values. So here we are, grid values. Okay, so we have two critical values, and that's step one taken care of. Step two is to divide the domain. Now the domain of this function is all real numbers, so divide the set of all real numbers up according to those critical values. So I'll usually just draw a quick number line real fast. And so there's the domain of our function, and 1 and 3. So 1 and 3. So if we have two critical values, that's going to give us 3 intervals to consider. We have negative infinity to 1, 1 to 3, and 3 to infinity. And we're using open intervals. Okay, open intervals when we're talking about intervals of increase and decrease. So now it's time to think about our chart. Okay, think about our chart. Let's see here. So there's going to be 3 intervals. Our first row is our intervals. And now we said we have negative infinity to 1. And then we have 1 to 3. And then we have 3 to infinity. Our next row of our chart is going to be your test points. Remember, it doesn't matter what number you pick. It just has to be an interior point, of course, because these are open intervals. So, 0 works here. 0 is always a nice one to pick if you can. 2 is between 1 and 3, and then maybe 4 over there. It doesn't have to be. I like to pick nice integers if you can, but if you can't pick a nice integer, then pick a fraction or pick a decimal number. It doesn't matter what number you pick, because the behavior will be consistent for all possible test values. I just try to pick ones that are nice computationally that I can use to do calculations in my head. Now, next row. This is where the process now is slightly different than in the previous video, because in college algebra you look at the sign of f, the sign of the function, but here we want the sign of the derivative f prime. And so now we take our test points and plug into the derivative. So I'm going to jot down the derivative just so we have it. F prime of x. I'm going to prefer the factored form. So here is the factored form right here. We factored the left-hand side, which was just the derivative. And that'll be easier to use with our test points. So x minus 3 times 3x minus 3. That's our derivative, just in different form, in factored form. So let's see. If you plug in a 0, what happens? All we care about is it positive or negative? We don't care what the exact answer is. Is it positive or is it negative? You plug in a 0, you get what? Negative 3 times negative 3, right? If you plug in a 0, which is a positive value. Okay? Now, what happens if you plug in 2? Okay, if you plug in 2, you get 2 minus 3, which is negative 1. And then you get, what, 2 times 3 is 6. 2 times 3 is 6 minus 3, so you get 3. So you get a negative. Okay? And then what about if you plug in a 4? Okay, if you plug in a 4, you get 4 minus 3 is 1. 4 times 3 is 12 minus 3 is what, 9? So you get a positive. Positive times positive gives you a positive result. Okay? So again, we don't care about the exact number, we just care about the result being positive or negative. Okay, so now we can state our results or our conclusion. Where the derivative is positive, the original function is increasing. So the derivative was positive on the intervals negative infinity to 1 and 3 to infinity. So we know the original function is increasing there. And the derivative was negative on the interval from 1 to 3. So we know the original function is decreasing. Okay, so we can say, for our final answer here, we can say that f is increasing on negative infinity to 1 union 3 to infinity, and f is decreasing on 1 to 3. And there you go. We have found the intervals of increase and decrease. And in the near future, we'll talk about using this to graph, to curve sketch. But for the time being, there are the intervals of increase and decrease. We know where the function's rising from left to right and where it's falling from left to right. Okay? Again, we're going to repeat this process with a new function. Okay, so here with example B, well, our first task is to find the critical values. So we need to find g prime and then solve g prime equals 0. So let's first do g prime. A few options here. I guess we could rewrite it and use the product rule. I'm just going to go ahead and use the quotient rule. It's really not a big deal here. Let's see what we can come up with. So we're going to take the derivative of the top function. So what's the derivative of natural log? X. It's 1 over x. So 1 over x times the bottom function, x, minus the derivative of the bottom function, 1, times the top function, natural log x, over the bottom function squared. We simplify this, of course. We get what? X over x simplifies to 1, so we get 1 minus natural log x over x squared is our derivative. Okay, let's see what we can come up with. So for critical values, we need to solve g prime of x equals 0. So 1 minus natural log x over x squared equals 0. Now remember, I've said this many times, we have a quotient set equal to 0. Only way a quotient can be 0 is if the numerator is 0. So all we have to do is consider 1 minus natural log x equals 0. And now we have a pretty straightforward logarithmic equation to solve. Since there's only one natural log, only one logarithmic term, what I'm going to do is I'm going to add it to both sides. So we get 1 equals natural log x. Okay, 1 equals natural log x. Now we can use the definition of a logarithm to solve. Because what does a logarithm mean? This natural log x equal 1 literally can be translated as the base, which is e for natural log, e to the first power equals x. That's exactly what 1 equals natural log x means. So there's our critical value. X equals e. Okay, now that's one critical value. Are there more? Well, we have to ask ourselves, is there any value that's not in the domain of the derivative that is in the domain of the original function? That is, are there any values for which the function is defined, for which g is defined, but g prime is not defined, where essentially where g is not differentiable? And you say, okay, look at the derivative here. Well, the derivative is not defined at 0, of course. But notice the original function is not defined at 0 also. They both have a denominator of 0. So they're both undefined at 0. And so there's no other candidates here. So we only have one critical value. Okay. Now, next step is to divide up the domain of the function according to our one critical value. Now, here's where you gotta be careful. A lot of students get into trouble this next step, because my instructions here are very clear. Step 2, divide the domain of the function into open intervals according to the critical values. Now, that means you have to recognize the domain of the function. What is the domain of g? Now, a lot of students just always default to all real numbers, negative infinity to infinity, kind of like example A. But natural log x over x does not have domain all real numbers. It has domain 0 to infinity, positive numbers. Okay, so you're thinking about your number line. Our number line starts at 0, and then we have our critical value e. Then, of course, it goes to infinity. Okay, but we only are considering positive numbers because that's our domain of the function. Okay, so let's build out our table. Let's maybe go here. Actually, that's not going to be room. A little too tight there. So let's scoot it over just a little bit. So we have our intervals. And again, we go from 0 to e. E is about 2.7 and change. Just a number. Don't let it freak you out. And then we have e to infinity. And then we pick our test points. Now, if e is about 2.7, well, what's a nice number between 0 and 2.7? Well, 1's a nice number. And again, if e is about 2.7, what's a nice number that's bigger than e? Well, maybe about 3 works. And then we're going to do the sine of, again, f, oh, it's not f, it's g this time, of g prime. Okay, well, where is g? G prime is right here. So let me box that off. Or I'll box it in red so I don't look at the wrong thing. It's easy to look like the wrong thing when you're doing this, and then you wind up with the wrong answer. Okay, so we're plugging into our derivative now. If you plug in, first of all, by the way, notice the denominator squared. What does that tell you about the denominator? Well, the denominator is always going to be positive because, first of all, the domain of this function is always positive. And so if we plug a 1 in, a positive number in, you square it, you're always going to get a positive number. So the denominator is always positive on our derivative. Okay? So regardless of what we plug in. Now, that means all we have to really consider is the numerator. Is the numerator positive or negative? Okay, so if we plug in a 1, what happens to the numerator? And essentially, what is 1 minus natural log of 1? Well, natural log of 1 is, anybody remember? 0. Natural log of 1 is 0. So 1 minus natural log of 1 is 1 minus 0 is just 1. What's a positive number? Okay. What about 3? If we plug in 3, well, 1 minus natural log of 3. What is natural log of 3? I don't know off the top of my head. So I guess we can use a calculator. Natural log of 3 is, if I could type in right, natural log of 3 is 1.09. So we have 1 minus approximately 1.09 is a negative number. And remember, the denominator is always positive, so all we're worried about is the negative on the numerator, and so the derivative is negative at our test point 3. So what does that tell us? That tells us our increasing and decreasing behavior. That tells us that where the derivative is positive, the function is increasing the original function, and where the derivative is negative, the original function is decreasing. Okay, it's decreasing. So there we have it. Okay, so now we can write our conclusions somewhere over here. Let's say that g is increasing. Actually, let me do this. I'm going to save some room. I'm going to go down a little further. We can say that g is increasing on, well, where is it? Where is the derivative positive? That was 0 to e. And g is decreasing on the other interval, which was e infinity. Interesting. We'll double check these on graphically with Desmos in just a minute. Let's look at C first and see what we can come up with. C, okay, it's a radical function, but it's also a product. So let's see what we can come up with. Of course, the first step is to find the critical values. So let's find h prime. Let's do the product rule. So we're going to have the derivative of the first function, x to the 2/3, times the second function, x minus 5, times the derivative of x minus 5 times the first function, x to the 2/3 power. Okay? Well, let's take these individual derivatives and we get, okay, what's the derivative of x to the 2/3? Well, you do the power rule, 2/3, x, and then you reduce the original power by 1, so you get negative 1/3 times x minus 5. And then, of course, oh, you know what? I didn't add a plus here. I didn't put a plus here. A plus, sorry about that. Don't lose the plus. Plus, big plus, x minus 5, the derivative of, well, that's just 1 times x to the 2/3, so 1 times x to the 2 power. Let's clean this up a little bit. We get, let's see, that's 2 over 3 x to the 1/3. We resolve that negative exponent. Oh, it's actually 2 times x minus 5 on the numerator. So 2 times x minus 5 plus x to the 2/3. Okay. Now, you know what? We probably should get a common denominator. We're going to have to do this soon enough. I'm going to go ahead and get a common denominator and combine those because that'll be the first step when we have to set it equal to 0 and solve. Okay, so let's see here. We can, oh, let me close that. That's bothering me. Windows is giving me an error message. Okay, so we can get a common denominator. So multiply this by, you know, that's over 1. So multiply by 3 x to the 1/3 over itself. I'm sorry, that's so messy. 3x to the 1/3. You know, we're multiplying by a special strategic version of 1. Okay, so that's going to give me what? Well, our common denominator on the bottom is 3x to the 1/3. And our numerator is going to be, let's go ahead and distribute this. 2 times x minus 5, that's 2x minus 10. Plus, okay, what do you get when you take x to the 2/3 times x to the 1/3? You have the same base, different exponents, you add the exponents. What's 2/3 plus 1/3? X to the first power. So you get 3 x to the first power, so 3x. So our derivative ends up being actually pretty nice. That's going to be what? 5x, 2x plus 3x, 5x minus 10 over 3x to the 1/3. So that derivative took a little more work than our others, but that's, you know, no big deal. There's our derivative, and now we need to find the critical values. That's our first step. We're only halfway through our first step, so we need to finish our critical value task, which means we need to solve h prime equals 0. And now that we have this factored form, that means we have 5x minus 10 over 3x to the 1/3 equals 0. Again, we have a quotient equals 0. The only way, oh, you know what? Oh, we gotta talk, sorry. Actually, no, we're good. I'll do that in a sec. The only way the quotient can be 0 is if the numerator is 0. So instead of solving 5x minus 10 over 3x to the 1/3 power equals 0, we can just simply solve 5x minus 10 equals 0, which of course has a super easy solution of, you know, add 10 to both sides, divide by 5, you get x equals 2. So there is a critical value. Critical value. It's a solution to h prime equals 0. Now, where I almost started talking a moment ago, and I figure we can do it now, though, is we also have to consider the fact that you might have a critical value that is the result of a cusp or a vertical tangent line. That is, it's a place where a point, a value of x, where the derivative is undefined, but the original function is defined. And I think we do have one of those, because here, let's look at the derivative. Here, I'll go ahead and highlight it here. Here, oh, well, nope. Here is the derivative. Okay, what do you notice about the domain of the derivative compared to the domain of the original function h? What is not in the derivative of h prime? 0. Okay, 0 cannot go in the denominator. Division by 0 is undefined. But is 0 in the domain of the original function? That's the question. And the answer is yes. You can plug a 0 into h. h of 0 is in fact 0, because 0 to the 2/3 is 0, times 0 minus 5, so 0 times negative 5 is just 0. So 0 is in the domain of the original function, but 0 is not in the domain of the derivative. That means the function is defined, but not differentiable at x equals 0. Therefore, 0 is a critical value. So x equals 0 is not a solution to h prime equals 0, but it's a value for which the derivative is undefined, but the original function is defined, and that was the second part of our critical value definition. So we have two critical values. We have 2 and 0. Now, the next step is to divide up the domain of your function according to your critical values. So the question is, what is the domain of our function? Well, looking back at h there at the top of the page, all real numbers. I think we've talked about this before. When you take the cube root of a number, there is no trouble domain-wise. In fact, if x to the 2/3, we're squaring a number and then taking the cube root. There is no issue with domain. So the domain for this function h is all real numbers. And so we're going to divide up the domain at 0 and 2. And we're going to negative infinity on the left, positive infinity on the right. So let's build out our chart. And so we have what? Intervals. Okay, so we have negative infinity to 0. And we have 0 to 2. Then we have what? 2 to infinity. Now we pick test points on our next step. Now remember, we want to pick ones that are convenient, but we can really pick any number, whether it's a decimal or a fraction or whatever. But here we can pick convenient ones. I mean, -1 is probably the convenient one for the first interval, +1 for the second interval, and maybe 3. And you could pick 3 million if you wanted to, but it's not going to be as easy to work in your head. I mean, just like with the first interval, you could have picked -pi. That's a number that lives in negative infinity to 0. But again, we want to pick numbers that are easy to calculate with in our head. Okay, so now what we do is we look at the sign of the derivative h prime. So I have the derivative boxed off there in red. There's really no shortcut here. The denominator can be positive or negative. The numerator can be positive or negative. So let's just see what happens when we plug in a -1. So if you plug in a -1, you have -5 minus 10. So the top is negative. So the top is negative. If you plug in -1, the cube root of -1 is negative. So the bottom is negative. Well, so we have a negative number divided by a negative number, which leads to an overall positive quotient. Okay. What about if we plug in +1? If we plug in +1, we get 5 minus 10. The numerator is negative. But the cube root of 1 is 1. So the denominator is positive. So in this case, we get a positive denominator, negative numerator, which leads to an overall negative quotient. And then what about 3? If we plug in 3, we get 5 times 3 is 15 minus 10, so we get a positive value on the numerator, +5. And on the denominator, we get the cube root of +3 is just some number. It's just some positive number. And so the top and the bottom are positive in this case, and so we get a positive result. And then we just read off our results. Okay. Once we have our sign behavior, we know that where the derivative was positive, the original function is increasing. Where it was negative, it's decreasing. And where it's positive, we are increasing again. And so now we have our intervals of increase and decrease. So our conclusion here is that h is increasing on, let's see, that was negative infinity to 0, union to infinity, and h is decreasing on, the interval was 0, 2. Okay, let's check these three using our using Desmos. Again, it's always a super good idea to check yourself using a graphing calculator, and actually not just any old graphing calculator, because handheld graphing calculators are not so great. But using Desmos, if you have the internet available to you while you're doing your homework, which I guess you should because you're doing it online, you can super easy check with a very nice graph to make sure that your solutions are correct. So let's see, the first function is x times x minus 3 squared minus 2. I'm going to go ahead and type in all the functions. So I'll have to do it again, and I'll hide them as we need to. X to the 2/3 times x minus 5. Okay, and let's hide a couple of the first, except for the first. All right, so here's the first function. And let's see about, let's not maximize the window. There it is. Okay. Oh, there's our function. So that's f of x equals x times x minus 3 squared minus 2. Now, what was our conclusion? Our conclusion, let me scroll down just a little bit. There we go. Our conclusion was the function was increasing from negative infinity to 1, and then from 3 to infinity. And notice, okay, the function is indeed rising from left to right, forever from the left until you get to 1, and then forever after 3, which is exactly negative infinity to 1, union 3 to infinity. And notice the only place where the function is decreasing, where it's falling from left to right, is between 1 and 3, which is exactly what our conclusion was. The function was decreasing on the interval 1 to 3. So our solution was precisely correct there. All right, what about the second function? Natural log x over x. Oh, this one's right in the middle of the page, so it's a little harder to have here. There we go. So there is natural log x over x. And notice, what did we say? Oh, we said it was increasing until you get to e, and it was decreasing afterwards. Okay, so looks like, we're increasing until we get to this peak right here. And hopefully you recognize 2.718 as a decimal approximation for e. So we are definitely increasing, rising from left to right until we get to e. And it's very subtle, but afterwards the function's falling. So we're decreasing after x equal e. Remember, it's not a bad idea to graph the derivative. If you call this, g of x, and then you tell Desmos to graph g prime of x, we can actually look at the derivative. Here, I'll make it dashed. So notice that the derivative does indeed dip below the x-axis at e, which is the precise location of that point where the function transitions from increasing to decreasing. And notice that the derivative, the purple dashed curve, is above the x-axis over the exact same domain that the blue original function is increasing. Likewise, the purple dashed function, the derivative, is below the x-axis where the original blue function is decreasing. That's what we've done by filling this chart out. We've determined where the derivative, the purple dashed function, is above or below the x-axis, which told us where the original function was either increasing or decreasing. Okay, last one was the one with the radical in it. Let's see here. Let's call that h, and then we'll graph the derivative 2. Okay, let's turn the derivative off. That's kind of crazy. There is the graph of h. And what did we figure out? We said that h was increasing from negative infinity to 0. So yeah, that's true. The function is rising from left to right, from starting from way over negative infinity until you get to 0. Notice there is a cusp there, which we figured out that 0 is a critical value because the derivative was undefined, but the original function was defined. Okay, so increasing until you get to 0. And then we said it was increasing from 2 thereafter. So again, starting at 2 and then forever to the right, we are increasing again. And the only domain on which we're decreasing is between 0 and 2. And yeah, that does check out here because from 0 to 2, we are falling from left to right. We're decreasing, we're falling from left to right. Let's take a look at the derivative. Again, the derivative is purple dashed. So the derivative is over here on the top left. It's above the x-axis, which means that the original green function is increasing over that same domain. And yeah, so the derivative is above the x-axis from negative infinity to 0, which means the original function is increasing from negative infinity to 0. So yes, that's correct. And then notice here that the purple is below the x-axis between 0 and 2, which means the original function is decreasing between 0 and 2. And then lastly, the purple dashed derivative is above the x-axis after 2 for the forever. And so notice that corresponds perfectly to the original green function being increasing thereafter from 2 to infinity. So again, what we're doing here by filling out our chart is we're finding where the derivative function is positive or negative, above the x-axis or below the x-axis. And that allows us to use a theorem from the previous video which says, hey, if the derivative is positive, then that means the function is increasing. If the derivative is negative, the function is decreasing. And if the derivative is 0, then the function is constant. So the function is constant at that point, just briefly for a single point. And again, we describe all of our answers using openings. Okay, so I hope this has been helpful. We're going to do several more examples of these. In fact, we're going to do this exact same process several more times, and we're going to continue to build on this process, and we're going to do it in a few different settings, but super important process. Again, it has its basis in algebra. Here we just put a calculus twist on it because we applied that process, this table process, we applied it simply with the derivative instead of the original function. Okay, so I hope this has been helpful. Again, if you want to be successful in this class, make sure you're studying to the tune of 2+ hours a day. Consistent daily practice is what this class takes, and of course, a little extra bit to that is ask for questions, ask for help when you have them. Reach out. Don't just sit there and bang your head against a wall. You gotta ask for help, whether that's the academic support center, whether it's you have other tutors, whether you want to talk to me during office hours. All of that's available. There's lots of resources available at the college. Just make sure to take advantage of the help that's here for you. And again, don't ever hesitate to reach out. I'm always available online, to help out, and of course during office hours. All right, we'll have more examples in the next video. I'll catch you then.